All right, so let's do this. We're going to pick up where we left off last time, which was talking about the stability of these dienes here. And the most important factor is what we covered last class period, the classification of these dienes as either being conjugated, isolated, or cumulated. All right, so remember, when we introduced all these dienes, we say that they're going to fall into one of these three families here. Either conjugated dienes, where they have that perfect double bond, double bond spacing. If they're further away than that, they would be classified as isolated dienes. And then lastly, if you got those back-to-back double bonds, those would be cumulated dienes. Conjugated dienes, because you have that network of p orbitals that those electrons can delocalize through, are the most stable. Isolated are just kind of in the middle. And then if you force those double bonds back to back, that's the least stable of those three, right? And that's going to be the most important factor in determining the stability of the dienes, is that classification. Again, most stable being conjugated, least stable being cumulated. All right, so we got these two other factors. So let's say that we got two conjugated dienes. How can we tell which one's more stable than the other one? Now we got to move down the list here to the next most important factor, which is the degree of substitution. All right, so what do I mean by degree of substitution? So first of all, this is something that you would have talked about in Chem 128A as well, specifically within the context of elimination reactions. So let's take a alkyl halide here, one of our substrates that undergoes elimination reactions. So we're going to treat this with a strong base here. It's going to undergo an elimination reaction, but depending on which one of its neighboring carbons lose a hydrogen, we could get two possible products here. We could have an alkene form on the end, or we could have an alkene form in the middle. All right, so our 1 or 2 butene here. And what you would have learned is that in these reactions, you don't get a 50-50 mix of these two products. One of these is your major product, and one of these is your minor product in this elimination reaction. Does anybody remember which one's which? Which one's our major product? Does anybody remember?
More stable.
The more stable one for sure. But which one's the more stable one here? The one on the right. Okay, so this one over here is more stable. So what is it that makes this more stable? So first of all, yes, it is our major product. It's our major product because it is more stable. But what feature is making it more stable is that it is more substituted. All right, so when we're talking about our degree of substitution, we're talking about the number of carbon neighbors that are bound to our sp2 hybridized carbons. All right, so what we call our degree of substitution. We're going to count total number of carbons bound to both of those sp2 hybridized carbons. All right, and so we can rank these from least stable to most stable. The least stable would be one of those terminal alkenes. So we're going to keep all of our examples here 6 carbons long. If I stick that carbon-carbon double bond on the very end, we would call this a monosubstituted alkene. All right, and how did I get that this was monosubstituted? I'm going to look at my two sp2 hybridized carbons, the ones that are about that carbon-carbon double bond, and I'm going to see that only one of them has this one carbon neighbor. So that's why that would be monosubstituted. If I take those same 6 carbons, but now I'm going to move that carbon-carbon double bond into one of these interior positions. This would be a di-substituted alkene. All right, because again, I'm going to look at my two sp2 hybridized carbons, and I'm going to count. This one has 1 neighbor, so that's 1. This one has another carbon neighbor, so that's 2. All right, so then everybody take a second. Sticking with our same 6 carbons, give me an example of a tri-substituted alkene. When we draw our carbon-carbon double bond, we got to make sure that we have 1, 2, 3 carbon neighbors. Sticking with my same 6 carbons, 1, 2, 3 carbon neighbors here. And then the most stable would be if we have a tetra-substituted, which is when all 4 of those bonds are carbons. All right, so this one's got 2, this one's got 2 for a total of 4. All right, so again, what we call our degree of substitution influences the stability of those alkenes. The less substituted alkene, the less stable. The more substituted alkene, the more stable. All right, so we said that classification is the first most important thing to look at. Then we look at degree of substitution. And again, more substituted implies more stable. All right, and then lastly, if you're tied in these first 2 categories, the tiebreaker is going to be the stereochemistry of those carbon-carbon double bonds. All right, so I kind of got lazy here with this elimination reaction. There's another 2-butene product that I could have drawn. Not the E stereoisomer, which is the one that I drew, but the Z stereoisomer. All right, and it turns out that this E stereoisomer here is still the more stable, rather the major product, implying it's the more stable. So what is it about this stereoisomer that's more stable than this stereoisomer? First of all, they're tied on degree of substitution, right? They're both di-substituted alkenes. So why would this one be more stable than this one? The structure. And what is it about the structure? Specifically in this one, these 2 methyl groups are pointed on opposite sides. And in this structure, these 2 methyl groups are pointed on the same side. all right? There's this general principle in chemistry called steric hindrance. Atoms are introverted. They don't like to be next to other atoms, right? So cramming these two groups next to one another on the same side of that double bond is necessarily more unfavorable than if you gave them more space and put them on opposite sides, right? So our Z stereoisomer, less stable because of steric hindrance. All right, so simply put, for our stereochemistry here, the last factor in our stability, these large groups like to be on opposite sides. And the bigger the group, the more true that is. In this case, they were two methyl groups. So you probably would see a little bit of this minor product in your reaction mixture. If they were more carbons, if they were propyl groups or something like that, all of a sudden you wouldn't see very much of this at all because it becomes that much less favorable depending on the size of these two groups that you're cramming next to one another. All right, but generally speaking, our principle that we want to have is that our large groups, they don't like to be next to one another. They like to be on opposite sides of that carbon-carbon double bond. So these are these three factors that are going to influence the stability of our dienes. The classification of those dienes, which one of these three categories it falls into. If two dienes fall into the same category, then we're going to look at the degree of substitution to figure out what's more stable. And if they're tied in those first two, then lastly, we're going to look at the stereochemistry of those alkenes. All right, so let's look at some examples here. You're going to rank these dienes here from least to most stable. So again, we're going to put these from least to most stable. The first thing we got to do is go in and classify them. This first diene here would be classified as what? Conjugated, cumulated, isolated. So this one's conjugated. What about my second one? Conjugated. Also conjugated. Got that perfect double bond, double bond spacing. And then what about the last one? So this one's isolated. So right off the bat, what can I put down on my little least to most stable spectrum here? This one's going to be in last place here, right? My isolated are less stable than my conjugated dienes. But now both of these are conjugated, so I got to go look at my degree of substitution. So let's look at this first one here. And we got to classify both of these double bonds here, right? They're both going to have different degrees of substitution. This one right here is what? Mono, di, tri, tetra, mono, right? So look, I'm going to look at both of my sp2 hybridized carbons. Only one of them has this one neighbor here. All right, there are no other carbons bound to those sp2 hybridized carbons. So this is a mono-substituted. And what about this one? So this one's di-substituted, right? So I'm only looking at its next door neighbors, for which it only has these 2 carbons. So I don't care what's happening further away than that. I'm only looking at how many carbons are bound to my sp2 hybridized carbons. So in this case, there are 2. We're going to jump to the other one. I want you to take a second, if you have not already, to classify these 2, or rather not classify, but determine the degree of substitution for those 2. All right, my first one, so this one's di-substituted, and what about this last one? Tri-substituted, right? If we're looking at these 2 carbons, we have 1, 2, 3 carbon neighbors now. All right, great. So, which one of these is going to be the most stable out of the 2? The one on the left or the one on the right? The one on the right, because it's got that higher degree of substitution. So this one's going to be sitting somewhere in the middle. Okay? So again, first thing we did was classify them when we were tied, then we looked at our degree of substitution. All right, you're going to do this last set of examples here for me. Same idea, you're going to classify you're going to rank these from least to most stable. All right, so step 1 is that classification. Our first one here is which category? Conjugated. The second one? Isolated. And the last one? Also isolated. All right, so that means that we can put in first place, the most stable, our conjugated diene. All right, let's go through and classify these alkenes here. This one here is mono, di, tri, tetrasubstituted. So this is mono-substituted. And what about the second double bond? Di-substituted. But if I look over here, I get the same thing. A mono-substituted and a di-substituted. So now they're tied. So now what am I going to do? Stereochemistry. All right, so this first double bond here, is this E or Z stereochemistry?
Neither.
Nice. All right, trick question, right? Why does this not have E nor Z stereochemistry? Because this one right here has two identical bonds, two hydrogens, right? So this one doesn't have any stereochemistry. But this one over here would be what? E or Z? E, they're pointed on opposite sides. This one would be Z. And so which one's going to be the least stable here, the E or the Z? The one where those two big groups are crammed next to each other in that Z conformation. All right, so again, we looked first at our classification, then we looked at our degree of substitution, and if that was all tied, then we broke that tie by looking at our stereochemistry. Cool. All right, so now we're going to go on and discuss our first reaction of our conjugated dienes. This is a reaction that's unique to these conjugated dienes, what's called a Diels-Alder reaction. All right, so I'm going to show you this reaction. You're just going to trust me, and then we're going to kind of pick it apart, and I'm going to show you how I got to that product. All right, so this is a reaction that occurs between a conjugated diene. So let's just use our simplest 1,3-butadiene. And what is called a dienephile. Right now, we're just going to use a simple alkene, and then we'll talk about the features that make up a good dienephile. All right, and first of all, that name dienephile, what the heck does that mean? What does that phile suffix mean? Something that loves something, right? An electrophile is something that loves electrons. A dienephile loves dienes, all right? So it's a reaction between a diene and something that loves dienes. All right, again, we'll talk about what features make a dienephile here in a bit. These Diels-Alder reactions will always form these six-membered rings. And this is the most important thing to keep in mind when you're drawing your products for these Diels-Alder reactions. You better have a six-membered ring in there because they always form a six-membered ring. Okay? We're using particularly simple molecules here. There are only these 6 carbons, so we only get a six-membered ring. But any Diels-Alder reaction will produce a six-membered ring. We might have some other carbons decorating that ring, all right? But we'll always get this six-membered ring, where 4 of those carbons make up 4 carbons in my ring. Rather, the 4 carbons about my diene make up those 4 carbons in my ring. And the 2 in my dienephile make up the other 2. Okay, so first of all, in order to see how we got from the left to the right here, how we went from products to reactants, importantly, we got to talk about our diene conformation. Okay, so when we took a look at our diene here, this is what we would call the S-trans conformation, where those 2 double bonds are pointed on opposite sides. And this is the most stable conformation of our conjugated diene here. All right? We're not allowed to rotate about our double bonds, right? That was the whole shtick between, the whole logic behind why they have stereochemistry in the first place is because the double bonds can't rotate. But we can rotate about our single bonds here. Okay? And so that's what we're going to do. We're going to rotate about that single bond So that now those two double bonds are located on the same side as one another. What we call the S-cis conformation. All right, and importantly, a molecule must rotate into the S-cis conformation in order to undergo a Diels-Alder reaction. If a molecule is locked in the S-cis conformation because there's a ring or something present, then it's really reactive in these Diels-Alder reactions. If it cannot go into the S-cis conformation, again, it's locked in some way with a ring, then it will not undergo Diels-Alder reactions. Every molecule must first rotate into this S-cis conformation in order for this Diels-Alder reaction to occur. All right, so then let's take this S-cis conformation and let's look at our reaction mechanism. This is what is called an electrocyclic reaction mechanism, because the electrons move in a circle. Okay, so again, let's take our S-cis molecule, or S-cis diene. We're going to kind of line it up in such a way that's going to make it a little bit easier to see what our products are. And then we're going to take our dienophile. Okay. What happens is we have these electrons, these pi electrons here that will move in a circle. This pair of pi electrons forms a new bond with that carbon. This pair of pi electrons forms a new bond with this carbon. And this pair of pi electrons jumps over. All right, so let's keep our carbons color-coded here. And another helpful thing that we're going to do here for our reactions in order to keep track from the left to the right is we're going to number the carbons about our carbon-carbon double bonds. This isn't like numbering for nomenclature's sake. It's just numbering these carbons that are involved in our reaction. In this case, there are only these 4, but as soon as we get things a little bit more complicated, we'll see why this is helpful here. All right, so it's always those 4 carbons in your conjugated diene that are going to be involved in our reaction. So now I'm going to do what I said, and I'm always going to start by drawing that 6-membered ring. For these carbons, which we had labeled 1 through 4, those come from my diene. The other 2 from that dienophile. All right, so these electrons moved in this circle here. So what exactly happened when that occurred? Well, let's note that now we have this new sigma bond that's formed. Right, I have a new bond between my orange and purple carbons. I know my colors. All right. I have another new sigma bond down here. Right, another new bond between the orange and purple carbons. But importantly, I'm missing one more thing here, which is that last arrow. This corresponds to a pi bond that has moved. Used to be between carbons 3 and 4, and now will be between carbons 2 and 3. And again, this is going to be the common feature that you'll see for all of your Diels-Alder reactions. We're going to make this more complicated by looking at uglier dienes and uglier dienophiles, but you always get this six-membered ring that's formed here, where you have two new sigma bonds and one moved pi bond. Okay? Your pi bond will always, if you do your numbering of your carbons about that diene, it will always have moved between carbons 2 and 3. Okay, so let's take this same sort of logic, but we're going to make it an uglier diene here. We'll keep it already in that S-cis conformation to make our lives a little easier. All right, everybody take a second and see if you can't draw me the product of this Diels-Alder reaction. All right, so again, we want to look at which carbons are involved in our reaction. The rest is just decoration here. So it's going to be these four in my conjugated diene. Again, to help keep things straight, I'm going to label these 1, 2, 3, 4. All right, as well as my 2 from my dienophile. I'm going to make my six-membered ring. Okay, again, 4 of those carbons have to have come from my conjugated diene, and the other 2 from my dienophile. This is where our little numbering scheme is going to be helpful here, because I'm missing a few things. First of all, I'm missing my carbons, right? So if I count carbons here, I have more on the left than I do on the right. Specifically, these 2 methyl groups here are missing. So where do they need to go on the other side? On carbons 2 and 3, right? That's what our numbering scheme is helpful for. Again, I'm not numbering like I would to name something. I'm just numbering to keep track of the carbons that are involved in this reaction. And what's the last thing I'm missing? That pi bond that's moved, right? And again, it's going to have moved to between carbons 2 and 3 in my product. All right? Cool. Now I said I was being nice by giving you this in the conformation already. So what if it wasn't in this S-cis conformation? What if instead I gave you this example? All right, and I said, give me my products here. The first thing we want to do is to rotate this into that proper conformation, right? Again, this is what we call the S-trans conformation. We want to rotate this into the S-cis conformation. All right, we can do our same idea here. We know it's these 4 carbons that are involved in our reaction. So we can start by drawing those 4 in our conformation that we need. right? What am I missing here? I need a carbon on which one? 4. All right, now here's the trick though. I could either have my carbon pointed up like this or pointed down like this, and those are 2 distinct molecules, right? So which one is it going to be? Well, importantly, I can rotate about that carbon-carbon single bond. I cannot rotate about my double bonds, which means that whatever my stereochemistry is up here, which is in this case that E stereochemistry, I better have that same stereochemistry down here as well, right? So do I point it up or do I point it down? Yeah. I would point it down so that I have that stereochemistry preserved. Cool. All right, so then finish this problem off here. What would be the product of my Diels-Alder reaction? We can take our dienophile and kind of rotate it to make it a little bit easier to see. All right, so I got my 6-membered ring here. I just need to decorate it the same on the right-hand side as on the left-hand side, meaning my purple carbons need those 2 methyl groups. Carbon 4 also needs a methyl group. And then lastly, I have to account for that movement of that pi bond to between carbons 2 and 3. Cool. All right. So we were looking at pretty simple dienophiles. Let's just talk about these dienophiles for a second. What makes a dienophile? So they must contain a pi bond. That electrocyclic mechanism there depends on that conjugated pi bond network of our diene, as well as the pi bond of our dienophile. So the example that we've looked at a ton are alkenes. Take our conjugated diene, that dienophile. We get that 6-membered ring. All right, but we could also use, instead of an alkene, an alkyne. They also have pi bonds. But they got an extra one. Importantly, only one of them will ever be used in my reaction here, which means my product here, I'll also have that one of those pi bonds remain between those 2 carbons from my dienophile. So our alkynes, we have retained one of those pi bonds from that dienophile. Now both of these would work as dienophiles. If you mix these two together, you would be able to get your Diels-Alder product. But truthfully, you'd have to crank up the temperature quite a bit, and your yield wouldn't necessarily be all that great. All right, so we can make these dienophiles even better. Our best dienophiles contain what are called electron withdrawing groups. And we'll actually talk a little bit more. We'll sort of expand this next chapter. All right, for right now, we're going to look at a diene, and we're going to stick an electron withdrawing group on it, a carbonyl group. Okay, this carbonyl group here can withdraw electrons through resonance. It pulls electrons onto that more electronegative atom, that oxygen. All right, so if we do our resonance jumps here, following our electron pushing arrows here, our other resonance contributor has this partial positive charge on that carbon that will help pull electrons from that conjugated diene. All right, so we could use a normal old alkene or alkyne, but you don't get great yield. You have to crank up quite the temperature. We can get a much better yield, much more reasonable reaction conditions by sticking an electron withdrawing group on that dienophile. All right, and in this case, we're going to leave it at carbonyls. We'll sort of expand that category. But the reason why that electron withdrawing group makes it more reactive is it withdraws electrons, pulls electrons onto itself, creating this partial positive charge on that carbon, which will help pull electrons from that neighboring diene when it does its Diels-Alder reaction. All right, and last thing we're going to note about these dienophiles is that the stereochemistry of those dienophiles is preserved in this Diels-Alder reaction. All right, so what do we mean by that? Well, we were talking about alkenes as our dienes. All right, so what if we started out with an alkene that had a specific stereochemistry? Here we have this cis diene or Z diene. Meaning that those two substituents there are on the same side. Well, when we get our six-membered ring that forms, Remember, our cyclohexanes can also have stereochemistry. All right, so which way are these two fluorines going to be pointed on my product? If they start out on the same side in my dienophile is what I meant, not diene, then we're going to get a cis ring, meaning that they're going to be both pointed in the same direction. So either both on a dash or both on a wedge, pointed in the same direction. All right, so the stereochemistry of that diene, of that dienophile is preserved in your Diels-Alder reaction. If you started out with a cis dienophile, you're going to get a cis ring. If you started out with a trans dienophile, you're going to get a trans ring, where these would be pointed on opposite sides. All right, so our first reaction of our conjugated dienes here are these Diels-Alder reactions. We're going to take our conjugated diene, react it with what we call a dienophile, and we're always going to form a six-membered ring here. We always have their same mechanism here for these Diels-Alder reactions, this electrocyclic mechanism, where we create two new sigma bonds, two new single bonds, and then one of our pi bonds moves over in our reaction here. Okay? In order for this reaction to occur, we got to take our diene and put it in what we call the S-cis conformation, and that makes it a little easier to see. Again, we got to have this strategy where we number our carbons that are involved in our reaction to help us match from the left to the right here. All right, and then lastly, we said that we can make our dienophile even better by sticking an electron withdrawing group on it, a carbonyl group that helps pull electrons onto that more electronegative oxygen, making the actual carbon better at accepting electrons from the diene. And then lastly, we're going to note that our stereochemistry of our dienophile is preserved in these reactions. So if you start out with a cis dienophile, you're going to get a cis ring. If you start out with a trans dienophile, you're going to get a trans ring. Great. All right, wonderful. We got one more set of reactions that we're going to learn next class period to close out our chapter on conjugated dienes here.
I have a question.
Yeah.
So you said on the for the diene, and it's on the Z stereochemistry, and you preserve the stereochemistry on the double bond. What if on that double bond it's not an E and it's a Z as well? So like you have a methyl group coming off of that double bond into like so the dienophile can't like.
Show me what you mean.